So let's dive in on the mechanism of forming citrate from oxaloacetate. This is where we incorporate our 2 carbons from acetyl-CoA into the 4-carbon oxaloacetate to get 6-carbon citrate. And as I previewed this with you last hour, I said this involves 2 different reactions. One is the aldol reaction, and the other is thioester hydrolysis. So looking at that first step, in the aldol reaction, we talked about how oxaloacetate with the ketone, which is a level 1 electrophile, is going to, the important functional group there is the ketone. The LUMO being the carbon-oxygen pi star, you expect a nucleophile to attack here, and you expect to break the carbon-oxygen pi bond. We'll use an enzyme-linked acid to facilitate that process, protonating the negatively charged oxygen as it forms. Yes?
Are we going to do an extra cut point because you didn't record?
Sadly, I pressed record, so maybe next time. But thank you for watching. All right. Then we need to use acetyl-CoA as a nucleophile. We're actually going to make an enolate. Remember, you make enolates by deprotonating at the alpha carbon adjacent to the carbonyl carbon. We've talked about how alpha protons are acidic because their conjugate bases are resonance stabilized. Of course, we'll need a base to do that deprotonation, and enzymes are useful for that. So, looking at the product, we can identify in here in purple the portion of our molecule that came from acetyl-CoA. We can identify, maybe I'll highlight in red here, the bond between alpha and beta carbons that we made in this process. So we can infer that we want an alpha carbon from acetyl-CoA to attack the carbonyl carbon of oxaloacetate. So with all that in mind, go ahead and tell me what the arrows should do. First will be what? Deprotonate what? Acetyl-CoA, the alpha hydrogen, then what? If I wanted to just draw the enolate, I would do that. You're always free to go stepwise if you want to. But if I want to show that enolate attacking, where is it going to attack? Ketone, carbonyl, carbon. What, did you not like that arrow? That's not any better. Okay. That arrow that we just did is, this one is a deprotonation arrow. This one is an addition arrow. Of course, we have to break the carbon-oxygen pi bond, and we could show that and draw an intermediate, or we can skip ahead and show the last protonation arrow. Okay, so this is how you can remember what the arrows should be. Pay attention to where you're trying to get to. Once you know that you need to have an enolate attack the ketone, this arrow is make the enolate, this arrow is addition to attack the ketone, this arrow is break the carbon-oxygen pi bond and pick up a proton, and this arrow is electrons from the bond between the proton and whatever it's bonded to go on to the conjugate base. Okay, so that's how you do an aldol reaction. You need 1, 2, 3, 4 arrows. Questions? Notice that the aldol product, you can tell it's an aldol product because this portion of the molecule was the enolate nucleophile. Count from the carbonyl carbon of what used to be the enolate, alpha, beta, and on the beta carbon there should be an OH group, and that OH group came from the carbonyl oxygen of your ketone electrophile. So with experience, you should be able to look at a beta hydroxycarbonyl compound and say, huh, that's an aldol product, and have some ideas of where it came from. Okay? All right, questions about the aldol? Second step is you look of this reaction, the next few steps, look at where we're starting. We have a thioester, which is a level 1 electrophile. And in the product, it's now a carboxylate, which is level 4. So already, even if you don't know whether the aldol should be in equilibrium or not, and it actually is, the aldol step is reversible. However, going from level 1 to level 4 should be strongly downhill. And in fact, this first step is irreversible. You're committed once you go through the first reaction. Whoops. So, thioester going to a carboxylate, that means that the thiolate leaving group is going to need to be replaced by an oxygen somehow. And this is where thioester hydrolysis comes in. So this one should require much less setup. Tell me what I'm going to do with water here. Deprotonate it to turn it into a nucleophile. That's often how we make things more nucleophilic in biology. The enzyme often deprotonates. Then what? Going to have this attack. Now OH minus is going to attack the carbonyl carbon. I'm attacking the pi star, so I have to break the carbon-oxygen pi bond. Notice that pattern. How often is that showing up here? Which is why we spent so much time on it a week and a half ago. That will get you to this intermediate. In the intermediate, you have a carbonyl carbon. Sorry. So in that intermediate, we've got the thiol leaving group, the oxygen nucleophile that just attacked. There's the carbonyl carbon, and there's the carbonyl oxygen. I'm realizing I'm changing shading schemes to illustrate what's going to happen with this molecule here. Hopefully that's not too challenging for you. This is a tetrahedral intermediate, and we can decide what happens next, even if we didn't know where we were supposed to go here, simply by asking which is the better leaving group, OH minus or RS minus. To do that, you can look up pKa's of conjugate acids, but it's the thiol SR minus that's the better leaving group. Electrons kick down, better leaving group leaves, and you end up with the step where OH has replaced the CoA thiol. If we were talking about what these steps were, this arrow here is an addition step, and these arrows here are elimination steps. Lastly, to get to citrate, this one's easy. You just need to deprotonate the acid. Okay, so now I'm hopeful that you're seeing why we spent time talking about these reactions before, because now you're seeing that they're used all the time in nature. Questions about how that happened, or what went on? Yeah?
Why does that process, why do you this is physiological pH, you just know it's pH.
Right, physiological pH, the pKa of that proton is 4, so at pH 7 it's going to be neutral. And also at pH 7, the thiol should also be neutral. Its pKa is 8, so at pH 7 its proton should still be on. It's just, I did it again, I lost the little thing on my Apple Pencil, oh well. Okay, yep, other questions? Good. So now that we've gone through that, it might be worth it if you're studying, not today or tomorrow, but once you finally come back online and are studying the new stuff, go ahead and practice this without somebody talking you through it, and then if you can practice it with the intermediates shown, and I'll give you a fresh copy of the quiz on the content page of Learning Suite, the problem set's going to ask you to do it without the intermediates shown. See if you can follow through yourself by pushing the arrows and drawing these. In other words, starting here, not having explicitly written out for you what this intermediate would be. And if you can practice it at that level, I think you'll have got it. All right, second is the steps where we convert citrate into isocitrate. And recall that our motivation for doing this, or nature's logic, is I want to get an alpha ketocarboxylate and or a beta ketocarboxylate. Right now, that OH is alpha to one carboxylate and beta to others, but it lacks, it's a tertiary alcohol, it lacks a hydride, it cannot be oxidized to a ketone. So if we want to make the alpha and beta ketocarboxylates to prepare for decarboxylation, that OH group has got to move. All right, and it turns out all you need are acidic and basic amino acid side chains, acidic and basic groups in the enzyme active site to facilitate this process. Conceptually, if you look at what's changed, by the way, with acid and base groups in these mechanisms, I'm using the acidic and basic side chains without showing you the products. In other words, these two are the acidic and basic side chains I need to do this step. These two are the ones I need to do the next step. So I know before in some of the quizzes for glycolysis, I was really, really careful about conjugate bases, conjugate acids. I haven't been here, and that's okay. You don't really need to be either. So if you look at the product, aconitate, this carbon-hydrogen bond is missing, and this OH group is missing. So propose a mechanism for that that only involves acid and base groups. What would you do? A clue would be to recognize that that proton is an alpha proton, and to remember that alpha protons are acidic. So if you're ever struggling with how to get started and you notice you've got an alpha proton there, just be thinking of that as one of the tools in your toolbox. Yeah, lone pairs on here can attack that proton. Then electrons will kick down, that's an elimination step, and OH leaves, picking up a proton as it leaves. And that's how you show the dehydration step. If you wanted to do this stepwise, you certainly could. For example, if I just removed the what I've highlighted as the red alpha proton, and then showed an intermediate, that intermediate would look like this. Negative charge on this carbon. Then that negatively charged carbon is going to act as a kicker offer to kick off OH minus as a leaving group. And probably it needs to pick up a proton either as it leaves or immediately after it leaves. So that's another way to sort of visualize what's going on. Okay, questions about the dehydration step? Yes?
Sorry, what makes the alpha carbon acidic?
The alpha carbon is acidic because I'll just draw the alpha carbon and the carbox and the adjacent carbonyl carbon. It's called an enolate, and the enolate is resonance stabilized. That negative charge is delocalized by resonance with the adjacent carbonyl oxygen. And things that have decently stable conjugate bases are more acidic.
So in the citrate, it's not yet acidic until we start the process, which is how it builds.
Right, well, sorry, you said in citrate it's not acidic until we start the process?
Yeah.
This citrate needs to bind the enzyme to have a base nearby that's strong enough to remove that alpha proton. Others? Yeah.
Remember the benchmark for like the pKa of a molecule that makes it a good leaving group versus not?
Right, so pKa's of conjugate acids that mean you have good leaving groups. In general, we've said things that have leaving groups with conjugate acids that are 16 or less are decent leaving groups. Protons that are alpha to carbonyls have pKa's in the range of, depending on the situation, around 20. That's not super low, but enzyme active sites can actually change that a little bit. And so enzymes do have bases that are strong enough to remove alpha protons. Okay. Now, with that in mind, you've seen a dehydration reaction. The next step is a hydration reaction, which is the exact reverse of a dehydration reaction. You almost need exactly the same arrows, but backwards. And I'll give you a hint. And actually, I think we want to keep the same color scheme that I used on the other sheet. The orange alpha proton gets removed and the beta hydroxy group leaves as a leaving group. Once you get here, this is where I told you that alpha beta unsaturated carbonyl compounds, that is carbonyls with a double bond between alpha and beta carbons, are electrophilic on the beta carbon. So the orange beta carbon could be attacked by a nucleophile, and the blue beta carbon could also be attacked by a nucleophile. If we used water as a nucleophile to attack the orange beta carbon, that would lead us back to citrate. If instead we attack the blue beta carbon, we will go on to isocitrate. And just to give you a hint, there's a proton present in isocitrate that's implied but not shown, but I'll just illustrate it there. So what I want you to do is, based on what you've learned from the dehydration reaction, see if you can figure out arrows with these enzyme basic and acidic groups as needed to get from a conatate to isocitrate. Okay, go ahead and take a few minutes to do that. I'll walk around and answer questions. other questions that I missed, anybody? Okay, anybody want to take a crack at the arrows?
I would love
You taking a crack at the arrows? Okay. I got confused.
Alrighty.
So the stakes are high now. If Matt makes a mistake, you guys lose an extra.
Whoa.
Just kidding. Okay.
If I get it right, 2 extra credit points.
Just for being annoying. Just for me being annoying, I'll have to give you. Okay, tell us what's going on there.
So we got the base enzyme attacking the hydrogen, which creates the extra link to go to the beta carbon or the alpha, whichever color you're looking at, breaking the double bond. And I mean, you could draw it to where it comes onto this carbon, but I decided to skip that step and I just drew it straight to attack the hydrogen here, making the lone pairs go onto the A enzyme.
Great, yeah, if you were going to draw the intermediate, your little arrow would have gone onto the blue alpha carbon.
That's what I said. I don't know what you're talking about.
Yeah, that's fine. It's fine, I was just teasing about the points. I thought we had a relationship as a class, right? But I realized that in a stressful test time, that kind of thing is just uncalled for, so I apologize. All right, good. Thank you, well done. All right, questions about the hydration step? And remember, this is beautiful because it puts the OH on a secondary carbon. And when you see isocitrate, you need to be thinking ready to oxidize. And that actually is our next reaction. So I've set up for you here isocitrate and NAD+. And I want you to do, I think you can do the first step of this on your own because I think you've seen this a couple of times. You've got an enzyme base that you can use. You've got NAD+ as a hydride acceptor. So I'm not going to set it up any more than that. See what you can do with this. Once you get to oxalosuccinate, let me know, and I'll tell you how the decarboxylation happens. It turns out there's a magnesium ion present to help. But yeah, go ahead and do the first oxidation step. questions? Anybody stuck? Yeah, that's great. Okay, anybody else feeling confident? Now that I've made the minus extra credit point. Yeah, come on down. Now that I made the minus extra credit point comment, we got nerves. I'm just kidding, I really wouldn't do that.
Okay. So, okay, what happens here is we take the electrons off of the base and they deprotonate the isocitrate, and then this bond will make a double bond on the oxygen, which then kicks off this hydrogen to this NAD plus, which makes it NADH, but then that removes this double bond here and moves that over here. And
Great.
Yeah.
Perfect. Couldn't have done that myself. All right, great. NAD plus mediated oxidation. Anytime you see it, it's going to be that mechanism basically. A base removes a proton on an OH group, and electrons kick down, and hydride gets delivered to NAD plus. So at this point, this becomes a mechanistic pattern that's in your toolbox. You won't necessarily need to be shown this anytime you see it in the future because you've already seen it and had some experience. Or rather, when somebody does show it, or when you see it when you see NAD8 plus in a future reaction mechanism or a future metabolic reaction, you'll have a pretty good idea of what's going on. Any questions about that? Yeah.
Is there a way you want us to show specifically the hydride leaving versus just the hydrogen? Like, should we circle the hydrogen and its electrons?
No, so I mean you can to show the hydride leaving. Is there any special way to show that? Do you need to circle the hydrogen and its electrons? No, that's actually implied by this arrow.
Okay. And then for the NAD plus, if you drew arrows like that and then you showed us its resonance form and the arrows pointing to the same spot but in resonance form,
Yeah.
like,
Yep, it's also totally acceptable to draw NAD plus like this with a plus on the carbon that's opposite the nitrogen, and then to show this arrow going there. Yep, great. Others? Okay, cool. So oxalosuccinate, just to review, once you get here, you have a ketone, and that ketone is alpha to the orange carbonyl carbon, but it is beta to the blue carbonyl carbon. And recall that beta keto acids spontaneously decarboxylate, and the reason they do is because the blue alpha carbon is a good leaving group. We're going to break this bond between the carbonyl carbon and the blue alpha carbon. And the thing that makes the blue alpha carbon a good leaving group is the presence of the beta keto group. So let's show you how this is. And it turns out in the enzyme, magnesium ion is in the enzyme active site and helps stabilize the leaving group when it leaves. So from our perspective, again, this blue carbonyl carbon becomes CO2. The alpha carbon is the one that's going to leave. This is the bond that's going to break. And then we've got a ketone on the beta carbon. So we'll say that the pink oxygen is our kicker offer. Electrons on that kicker offer kick down in an elimination reaction. And then the bond between carbonyl carbon and alpha carbon breaks. You can show this in two identical equivalent ways. I'm going to show you one, and then I'll show you the other. You can show electrons from the bond between carbon and alpha carbon kicking down to be just on the alpha carbon. If you did that, the structure that you would get would look like this. And I'm going to continue calling this the blue alpha carbon and the beta carbon. And then magnesium would still be here. Notice how this and this are resonance structures of each other. Notice that I can get from this resonance structure with a negative charge on the blue alpha carbon to this resonance structure with the negative charge on the oxygen simply by pushing arrows like that. Those two are equivalent resonance structures of each other. The one on top gives you the idea that the negatively charged oxygen is close to magnesium and interacting with it via an ion-ion interaction. Enzymes use ion-ion interactions to stabilize negative charges, and magnesium is great at this. So these are the arrows you would use if you wanted to go to the resonance structure below. I need to now redraw that here. All right, see if this works out. Oh, almost. Ew. Well, sort of close. All right. Now, if I want to instead push arrows in a way that goes directly to this one, what I would do on my pink kicker offer oxygen is the same thing we did before. Electrons kick down, and then we go, the bond between the blue carbonyl carbon and alpha carbon breaks. I kick it over here to form a pi bond between alpha and beta, and then I move the electrons from the carbon-oxygen pi bond out onto the oxygen. Either way, I get the same product, okay? So that's the loss of CO2, and because CO2 is a gas, readily dissolves in your blood and then you exhale it, this is irreversible. You lose CO2, you're not going back. So any step in the citric acid cycle where CO2 is lost, just because of entropy and CO2 going away into the gas phase or dissolving in your blood, there's no going back. So what you've got here as a product after the decarboxylation is an enolate, which is resonance stabilized. Now to get to the product, what do I need to do? What's changed from the enolate intermediate to this product? Yeah, just protonate on the alpha carbon, right? You can do that if you want to use the enolate resonance structure on the top. You kick the arrows here, then the bond between these two carbons breaks and the alpha carbon gets protonated. Alternatively, if you were going to use this resonance structure, you would simply draw an arrow from the lone pairs on the alpha carbon, from the lone pair on the alpha carbon to the hydrogen. Either one is okay. And that gives you alpha ketoglutarate. All right, good. Okay, so the next thing we need to talk about is just to review in words what happens to alpha ketoglutarate. So between now and next time, I would like, and this would actually, you think, oh, I can't do this, I've got to prepare for the test. Silly, doing this now will be preparation for the test because you've seen this reaction before with the pyruvate dehydrogenase complex. So what I want you to do before next time is I want you to take alpha ketoglutarate. I want you to use your notes on pyruvate, and if you want to abbreviate alpha ketoglutarate, you surely can. You can abbreviate it like this, and if you do that, you will see that it looks not so very much unlike pyruvate. I want you to take that molecule through the alpha ketoglutarate dehydrogenase complex in the same way that you did for pyruvate. We did that a couple lectures ago, then we did it again last time, so it's at least at a couple of places in your notes. See if you can do that again. That will be good practice for this exam, but will also help you see what goes on for alpha ketoglutarate. Okay? We'll review that at the beginning of class next time. Now, before you leave, I have a story to tell you, and it's off the record. So, and